So today we're very pleased to have Mimi Down, who is usually at the University of Illinois Chicago. Yes. For the past 2 years has been enjoying a life of luxury in Princeton, with all sorts of exciting mathematics going on. And we're very pleased that in between her many trips around the world, beginning to stop in Los Angeles. Today she will talk to us on singularity formation for models of fluids, unless you changed your mind.
I did, sorry.
Singularity formation.
Non-uniqueness.
It's turned to non-uniqueness.
Thank you very much, Susan, for the introduction and for the very kind invitation. Really happy to be here. Okay, so let me write down what I'm going to speak about. Forced equations. So there, in recent time, there are many investigations for fluid equations with the forcing. Okay, and we start with the favorite struggling, the Navier-Stokes equation, okay, and 3D. And I put a forcing here, and we are in an incompressible situation, and domain, I'm always on torus, so I don't have a boundary to worry about. And here we focus on 3D. So the one result I would like to start with, it's this non-uniqueness of weak solutions by the master and the Vickrell. Around this time, they used convex integration techniques to construct non-unique weak solutions. For 3D Navier-Stokes in the case of non-forced and not forced. And the solutions in the space time C0 in the space H beta for a very small beta. So the regularity is very limited. So the problem with this low regularity, it really comes from here, the dissipation. So for convex integration, we are adding high frequency oscillations, but when you look at the dissipation here for high frequency, it's very large. So in their approach, they basically treat the dissipation as an error term, but for high frequency, this is not very small. So that's really the limitation for this small beta, the regularity here. Okay. But with the forcing, so now it's this result by Barreto and Brew and Lambo. So that was recent. So what they showed, it's that when the forcing is present, they can construct non-unique Larry solutions for the 3D Navier-Stokes. And And here, so to remind you what is a Larry-Hope space, it's the finite energy. And entropy equal to, okay. So you can see that this, when you compare the two spaces here, it's much higher regularity here, okay. And so here they used a different approach, completely different approach. So they use this instability mechanism from Vishik's work. Okay. That's for oil and 2D. So this group, they managed to extend this 2D Euler result for to the 3D Navier-Stokes. So it was highly non-trivial. Okay, and again, the two approaches are very different, and of course here they have this flexibility caused by the forcing, and you might wonder, so naturally, how much is the equation relaxed by the forcing, right? But of course, it's hard to quantify. So, but certainly you do see some flexibility, and I'm going there. I'm going to show you in a little bit, okay? But I don't have an answer for this, but possibly we'll see some insights in the next few minutes, okay? Okay, so one more thing I want to mention is this very recent result by Stein and collaborators. So they look at Euler and with the forcing. So Euler is with a nu is 0, okay? And they construct non-unique weak solutions in space. If I'm right, it's Holder. I'm sorry. The alpha less than alpha, or it's no, it's a C. Okay, so this is very surprising because what? Because we know these on sagas, right? So here we have this on saga threshold, 1/3. So previously for Euler without forcing, 3D Euler, so without forcing. The on-saga was resolved, and in the same time you can so that's about energy conservation, but in the same time you get non-uniqueness as well. So but it's alpha less than 1/3. Okay. So again, the forcing really makes the difference. So I'm going back to this result again later. Okay, so now let me pause here, and I want to now trying to get some ideas towards this question. So in fact, I'm going to some Baudic model result here. So, Dowdic Navier-Stokes equation with the first one. Okay, so let me just tell you briefly about the Dowdic model. So we take the sort of Fourier coefficients, or more precisely, we take the projection, Littlewood Paley projection, the energy, okay? And here the AJs satisfy a infinite many system of ODs. So here the derivative is AJ theta. Okay, so the theta here is a parameter related to intermittency. And precisely for 3D model, 3D Navier-Stokes equation, I use D. Okay, so D is the intermittency dimension. Okay, and in 3D, it belongs here. Okay, so this parameter is related to intermittency. Okay, and let me add the forcing here. Okay, so this model, the Dowdic models have been studied extensively like a decade ago by Susan, Natasha, Alex, and lots of other people. Okay, and you pretty much know everything now about the Dowdic model. No, okay, no, okay. So there was a recent result by Will North and okay. So they proved non-uniqueness, non-unique Larry Hope for this forced Dowdic model. If this the D is less than 1, okay, so when the intermittency dimension is less than 1, and that's equivalent to theta greater than 2. Okay, so with for this particular one, and moreover, the solutions here satisfy energy identity. And for Navier-Stokes, like blood results, the energy inequality is not satisfied from the convex integration method. The energy you pump in energy to the systems, you don't have energy inequality. Here, those solutions satisfy energy identity, but of course, it's much simplified compared to original. So here we only count local interactions in Fourier space. Okay, so you only see interactions with previous and next shells. So now, just quickly, what is the idea of their proof? Okay, so what they did is that they assume there are two solutions, okay? And so there are two solutions, and they take the sum and then they take the difference and this U, the new variable, the pair satisfy the system. So let me just write out the major terms. So there are some quadratic terms, nonlinear terms, okay? And so that is the sum. So the force stays there. And the difference and non-linear terms. And for the difference equation, there's 0 on the right-hand side. Okay. So what they did is that they construct just once, not like convex integration, you have to do iteration, you have to do lots of construction. So here they construct in one step the two sequences satisfying the number 2. Okay. And then why that's possible? It's possible because here really it's so simplified. Here it's only local interactions in the nonlinear terms. So the profiles they choose and the UJ, it's supported just a short time interval like UJ and the VJ longer. So it's it uses this local interaction. So they were able to just construct a sequence by hand, satisfying this second equation. Okay, and then they take this constructed sequence to 1 here. Whatever on the left hand side, it's the force. So you do, now you see kind of this flexibility, right? There, it's all the error terms, or all of them. That's the forcing. Okay. So now, with Susan, we applied this to a MHD diodic model. On the left. Here, right. So actually, the other side, they proved the uniqueness. Yes. Right. Oh, you mean negative? Right. Oh, yeah, right. But we are talking about it works for all of them. Yes, but basically.
Something accounting for U ratio and square J, for U
Here,
yeah,
those.
Equation.
Actually, that's the no. So when you multiply AJ to this equation, you'll see consolation. So you put it here and here AJ, you see this telescope summation. So energy is conserved formally. So that so right. So the it's yeah. So the two together comes from here, but we with the assumption interactions only with the previous and next shells.
Okay, looking for lambda J.
Sorry, yes, that's the frequency number we take.
So the paper is responding to the gradient.
Yes, 1D, right, exactly. Yeah.
I have a question about the FJ.
Oh,
So
okay.
for the statement of the non-uniqueness.
Right.
So is it given f different from 0, they have your non-uniqueness, or there exists an f?
There exists an F.
There
Yeah, right,
exists an
right,
F,
right,
okay.
exactly.
The app is constructed.
Right, yes.
When f is zero, solutions are regular even when g is above zero. That was
Right.
or bottom,
Right. Yes, above
So basically, there is a reason, right?
it, it's above one. I mean,
No, above one is trivial because it feels like it becomes
right.
critical.
Right. They extended the region a little bit.
Not a little bit, they went basically all the way down to d equals to zero. So without force,
Okay.
solutions are regular and unique
Okay.
when d is above zero.
Okay.
And
Yeah,
the
right.
force basically is one uniqueness.
Is right. So here, come back to the question: how much your system's relaxed by, by putting a force in there? So I don't have an answer. But you do see, like, yes, it's very different when you have a force in the result. It's really different. Okay, so yeah. So I was about to say that with Susan we did so we look at force diodic MHD or magnetic hydrodynamics. I'm not going to write it down the system here. Similar to Navier-Stokes static model, but more complicated because of interactions, more complicated. And here the force is really just in one equation. Okay, so the AJs, so force is here and not in the magnetic. There's no force in here. Okay, so here it's a coupled system. So for this, and we also have the similar nonlinear terms. Showed that if the intermittency is less than 1, we have non-unique. So non-unique array of solutions. So here, why we care about this? We just found a very, like some kind of similarity between this difference sum system and naturally the MHD system. There's a similarity. And another similarity is that we have two variables here, two equations, so we have more freedom. Okay, so I won't get into details here. So now I actually want to pose the second question. Hopefully I'll get some genius ideas from the audience. So here, can we actually write to, let's say, lift this method for dyadic models to the original, to the PDEs. So for dyadic models, really we are dealing with the ODEs. Okay. So now let me formulate it, this question precisely. So again, we use Navier-Stokes as example. Okay. So now let's say we assume we have two solutions, U and U tilde. Okay, yeah. We have two solutions of forced memory space. Okay. And we take the sum and we take the difference. Okay, and I'm going to write out the system satisfied by the pair PM. Okay, so now the P is satisfied. And I'm going to use a different notation for the pressure now. The force here. And so the dissipation is here too. And okay, so that's the sum difference system. So now you try to ask the question: is it possible actually back to PNM satisfying the second PDE? Right? So let me put, or just should I even say approach? I have no idea how to do it. So one, construct PM now satisfying two, right? And then you plug it back to the first equation and you get a force in the right space. It's certainly much harder than the Dowdick model, but is it impossible? I don't know. So at the moment, I don't have much ideas, much thought. Oh, yes. So here we need to put the initially it's 0, but it's not always 0.
About 3. Minus 1.
It's two positive signs. So if it's a minus, then it's MHD. Yeah. So yeah.
How do you take P equals 0?
You take P equal to 0. Okay. Okay. And then do we get two solutions? P to the sum. So means you get 2 with a negative sign, opposite sign. That would be very nice sometimes.
Yeah. You can construct the solution MT for the second equation, and that one, those can take.
Okay. Oh, right. So here, that's what you're going to solve, right? So you're going to, it's a 0, you're going to solve this. And here you have the
It's hard. Yeah.
okay. So yeah. So some of the people I talked to, they suggest a spectral method for this equation to construct a pair satisfying the second one. But again, with the transport one, it's doable. But with this one, it's difficult with the spectral method. Okay, so now let's see maybe approach 2. actually, we come back to convex integration and how to do it. So I think with Susan, we were thinking about this after the MHD result, like how to implement a convex integration scheme for this formulation. So there is one way. You put another forcing here. Okay, so now we have this freedom of forcing in each equation. So we can construct, so we have this underdetermined and actually much underdetermined. So we can construct an initial pair P M. Okay, the initial pair, not initial data. That is fine. Both 1 and 2 with some kind of forcing F and G. So we have this freedom to do that. And M is not 0, but at initial time it's 0. So we have this freedom to do that. And then we apply convex integration only to the second equation to reduce the forcing G. Okay. So we just need to reduce the forcing G. When G goes to 0, then we come back to this coupled system with the forcing in the first equation, and which is equivalent to two distinct solutions here, okay, with the forcing for the Navier-Stokes. Okay, so can we reproduce the result of the ABC? No, so reproduce the ABC results, the Arboretum, Brew, and Colombo. So actually, it's
Movement of smooth all the time. How can you obtain anything smooth with convex integration?
I told you no.
Oh.
Right. So yeah, so possibly maybe you can get solutions with a regularity a bit higher than what Vlad and Tristan did, but to produce this one, Larry, hope no. Okay, so but we do find applications. So now let me clock. Does it work? It's okay.
Just as one arm.
Yes.
So now let's look at this idea. For SQG with the forcing, and I'm going to put it stationary. So let's look at SQG. Inviscid. And here it's in 2D. So let's put it on torus. And U is given by theta through this non-local operator. So here lambda is the half modulus. Okay, so as I said, we look at stationary. So let me put it away. So there is a result by and you. So they showed that let me put the general forcing here. So in my case, no forcing. They got non-unique weak solutions. And so such that this one, it's in the space alpha less than half plus 1/6. I mean, we can do the math, what it is. But I'll keep it this way for now. Okay. So here, I want to, yeah, let me actually write out the result. So that's around this time. So now with the forcing, with my student, so we, let's put it, there exists a forcing in C -half and a bit worse, so minus epsilon, and which can be arbitrarily small. Such that there are no unique weak solutions. The regularity is in, say, alpha less than half plus 1/4. It's a bit higher regularity, but of course with a forcing here. And that was recent. So in the rest of the time, I want to show you how that some different systems helped with this, okay, to get this higher regularity non-unique solutions. But I want to go from the original one without forces. I'll just show you heuristics. Okay, so well, when there's no forcing. Okay. So convex integration is a process of approximating iteration. So we look at a relaxed system, and here, all right, divergence and gradient, and I use R. Well, I'll use R, but now R is not a tensor. R is a scalar with a function. RQ. Okay. And actually, why we put two derivatives here? So because we are able to, and we are able to do this, usually you gain something. Okay. So now let me actually say we can work at a different level. So here you can write as divergence. So the construction is not at the level of theta or u. Instead, we'll take eta. It's this operator acting on theta q. Okay. And then if you recall uq, it's this one, and theta q. So you see that is here and eta q. And theta q is lambda of eta q. So we are going to work on the level. So now I'm going to rewrite it. UQ is this one, and theta q is here, and its gradient RQ. Of course, you might have terms like this, right? But let's forget about them, because when you apply divergence, that's gone. So I'll just to be brief, I just keep it this way. So the convex integration is that you want to construct the next one somehow by adding a high frequency part on the previous level. Okay, so you want to construct this, and then you produce a new portion. Ideally, you hope this one in some norm it's strictly less than the previous one. So you can keep going. And then you take the limit. In a limit case, you get a solution to the unforced, like no force on the right. Okay. Okay, so now let me write out the arc, the next level RQ, what would it satisfies? So the gradient of RQ plus 1, it has this main part it is like this. So here it's just algebra. You can trust me unless I make mistakes. So that's the new stress. And two other terms that comes from the linear term. One is eta q and w q plus 1. Another one is w q plus 1 and beta q. Okay, so the constructions are here. We try to get to the right increment such that this one is close to 0. It's small. Okay, so now from here we get our energy level. That's what I think referred by EZ from the very beginning. So from there we set our scaling. So now I'm going to introduce some numbers that standard convex integration notation. So for some large lambda and a constant b and a q, we take the integer and there's delta q for a beta. So here b is greater than 1. And let's look at it this way. It's very close to 1. Okay, I'll put it this way. And the beta is here. Okay. And that lambda is some big number. So here, that's the frequency parameter. And this is the size. We're going to measure those terms there. So from here, I prescribe RQ. I'll take the norm C0 or L infinity. So in the construction, we don't use intermittent building blocks. So any LP would give you the same result. So I just don't put anything here. Maybe I should put 1. So this one, I see, okay, we set the scaling to be delta Q. And then from there, the gradient RQ is similar to here. Okay, so eventually we apply, they are localized. So eventually we apply this anti-gradient operator. So really you can put it this way. I just remove any of them. All here is fixed. Okay, so that's one derivative. And the frequency of next level, it grows to this one. And I have this WQ plus 1 squared. And here it's delta Q. So now I get a WQ plus 1 size is
The WQ localized?
yes, in the construction, yes. So here I get lambda negative half and delta Q half. Okay. Okay, so if we do the right construction, this can be made small. So now, what is the next step? So we want, we want the next level Q plus 1, the size can get smaller. So move to here, for example. Okay, so that's what we want. So now we have two other terms. In the stationary situation, the scaling something. Okay, so I just look at one term. So I'm going to look at the other one. Sorry, it is one of them. This eta Q. And here. Okay. And because I'm going to apply a so here it's an anti-gradient operator. So the degree is -1. Okay. Apply on this and look at the size. So again, they are localized. So here, this is degree -1. It gives me here, and that's on this. I get the derivative lambda Q, and the eta Q is we would take the same. So here, if I should put eta Q plus 1, but that's again make this assumption or inductive assumption. So here, eta Q would be the lambda Q according here, -1/2 and delta Q -1/2. And this one I get one derivative and WQ plus 1, it's this one. It's lambda Q plus 1 -1/2 delta Q. Okay, so we want this one to be bounded from above by the one we want. Okay, so that's what we want. So now let's look. Okay, so let's do the simple algebra. I'll put everything in the base of lambda Q. So the lambda Q next level, due to this choice, I get a -b, and here +1 and a +1/2. Okay. Lambda Q. Yes, okay. And this is delta. Delta Q -1. So from there, I get a -1/2 beta and B, because it's the previous one. And then this one, oh, it just got canceled. I mean, half. That's half B. So these two. And here, it's negative of beta. Okay. Less than delta. I mean, in the base of lambda Q is negative beta and times B. Okay. So now that's what we need. So means index should be less than 0. Okay. And okay, so now again, just I'm going to make it like this, minus beta, so beta. And why do I do this? Because you'll see we're going to use the conditions here. And I have a -1/2 B plus a 1. So we have B -1 b minus 1 from these two, b minus 1. And then the choice of b greater than 1 gives us okay. So I get, is that right? Okay. So beta less than half. There was a sign problem. It should be plus, actually. Should it be plus? There was a sign problem. Yeah. Okay, so now because b is very, very close to 1, that's like this, so you get a third. Okay. So you need the condition of beta is less than 1/3. So now come back to the regularity level. So this is the eta, and I want so now let me again the eta q, the level is the lambda q. So here lambda q negative half, and delta q minus 1/2. So this is C0. Now we want to check the C alpha. So you put C alpha, and you would get a extra lambda K alpha. And you want this to be bounded. Okay, so now again, we do the simple algebra. Put everything with base lambda Q, beta and the B, because here, plus alpha. So we want index to be negative. So you see alpha is less than half plus beta over 2b. And again, if that choice, this, you take a b close to 1. Okay, you get this half is 6. Okay, I need 5 minutes. So this is the heuristics for what they did without forcing. So now with the force, and we apply, I want to see this. So we apply the system of difference and the sum. And see what's where did we gain that a little bit more regularity. So now the heuristics with the force. So again, I'm going to assume there are 2 solutions, and we take the sum and the difference. Okay, then you can notice that A times the sum of these 2, the Q times the difference of the next 2. Okay, and then the equation satisfied by PM. So basically the same thing as I wrote down earlier for Navier-Stokes. So I'll put it, oh, I'm in stationary. So I only have this. Okay, so P and P M and with the A forcing. I would choose to put it this way, so maybe I should use a different notation. And the other one is P P, no forcing. And I would put a Q and a Q. And now we do convex integration. And to relax it, I'll put one more forcing here. So the goal is to reduce this one, the 2. Okay. Okay. So now we do a 1 stage, 2 steps. design here, and I'll explain what it means. So actually we start from a 0Q and for only even Q, okay? And for each even Q, we do 2 steps construction. And so now I'm going to construct ones. So I need to construct and that, and I need to construct a 2 plus 2, 2 plus 2, okay? And here is what we do. So here it's PQ minus some increment up to our choice. And here it's MQ plus this one. And the next one, it's 2 plus 1 plus 2. And here it's plus. So I didn't make a mistake about the signs. We are choosing in this way, especially. Okay, so now this and this, they are constructed. Okay, and now with this construction, you notice that when you add the 2, right, we get eta q plus 1. And because of the cancellation, you get this, okay? And these 2, if we subtract the 2, this is gone, and we get at next level, the tilde, the difference is the tilde previous one. And that's the key to gain. And I just need maybe 2 minutes to write down. So I'll show you what is the new force. So the, I used the L. So this one, so we need the form of the 2. Okay. So we get the same, the main, here it's minus 2, this W. And this one, it's plus Q plus 2. Q plus 2. And with the other terms, the linear ones, let me only write out 1. I erased that. So it's this one. So here it's the eta to the Q. Yes, it's eta to the Q. And WQ plus 1. And then I have one more term, basically switch the 2 operator. And here I get 2 plus 1, no tilde. Okay, so these 2 are essentially the same as before, means when we set up the scaling, we set up the same scaling. But now, again, it's here because of this construction. So for even Q, this is equal to the previous one. And for odd Q, this is equal to the previous one. So that's where you get more regularity, and you can do the same heuristics as before, and you get a bit better. And this is just the same thing as what Stan did in the Euler paper. So here it's in the paper for but of course, here we only did it for stationary. For time-dependent one, we can do it too, because this is a very general. Just for time-dependent one, you need to apply time cutoff and flow map and gluing. It's much more complicated. Okay, so again, the question is how much the systems relaxed due to the forcing, I don't know. Hopefully, yeah, you have some good ideas to tell. Thank you.